There are two things that we fit in a separate category all by themselves. They actually apply to multiple different categories, but they're very different from everything else. And these two things are springs and pendulums. So this video is going to talk about springs, and then I have another video that's going to talk about pendulums. So for springs, they have their own special formulas. The first one we're going to talk about is spring force. So force of a spring, and that's equal to negative kx. The negative is just a vector quantity. When we talk about springs, we talk about multiple different types of springs. So we have compression springs and we have expansion springs, and every single spring has its own constant. So that's this k is the spring constant. Spring constants tell you how much force is necessary in order to move it a distance. And so for this one, this would be a compression spring, and this one would be an expansion spring. So as we apply a force to either of them, it doesn't matter, the distance that it's compressed multiplied by that spring constant equals the amount of force supplied. As we get springs in motion, you can have hanging springs or you can have springs attached to a wall. We're just going to go ahead and do on a horizontal plane. So if it's on a, I know this looks vertical, but pretend it's horizontal. So on a horizontal plane, let's say that I have a spring, and this is going to be a succession of motion, but let's say that I have a spring that I'm starting out being compressed. So let's say I took this expansion spring and I compressed it all the way. I have a block on the end. And then I let it go. And as I let it go, it's going to speed up and be very fast at a certain point. And then once it's past that point, it's going to slow down and stop. And then at that point, it's fully expanded. And so it's going to want to come back to where it was before. So it's going to go through that again so that it's compressed all the way. We talked about a roller coaster when we talked about potential and kinetic energy. And for the spring, it's very similar. So at this point, I have total potential energy. And the reason I have total potential energy is because it's totally compressed and it's ready to spring. Here is where I have total kinetic energy. This is also what we call our equilibrium point. So if the spring had not been compressed initially, then this is where it would sit by itself. It would be happy at that point, not moving. So it's our total kinetic energy because it reaches as fast as possible that it's going to go, and then it begins to slow down until it's stretched to its limit. At this stretch to its limit, it's back to total potential energy. And then we start moving again, and we're going back, and we're going faster and faster until we reach that equilibrium, and then I'm slowing down until I get the total compression. So I'm back to total kinetic energy, and then back to total potential energy. Kinetic energy is always 1/2 mass times velocity squared. Always. Potential energy, on the other hand, is equal to 1/2 kx squared. So this is our spring potential energy. And here we have that k again, which is the spring constant. So that's very important when we're talking about different springs. The spring constant is not a single number. It's going to change just like the coefficient of friction depending on the substance that we're talking about. But remember that here where you have total kinetic energy, this is also your equilibrium point, where it's going to sit when it's not moving.